Hello and welcome to the 181 video on k-means clustering. Clustering is a new problem that we haven't talked about very much, but it occurs when you have a bunch of data and we want to find natural groups to split up our data into. This is an unsupervised problem as opposed to any of the problems that we've encountered before because the data doesn't actually have any preset classes. When we're talking about things like binary linear classification or SVMs, we're usually talking about data where we get it and it's labeled as, these people had a disease, these people don't have a disease, or whatever label we're trying to assign to the data. But in an unsupervised problem, we don't get that. We don't get those labels, and we have to go ahead and assign groups to the data ourselves. So on the left here, we might want to separate the data into these two groups, and then we'll have a model that, given a new data point, can predict which group we're going to put it into. And you might be wondering, what are some real-world applications of this? A lot of movie or song recommendation systems will use techniques like this. So what is our high-level strategy? Well, as the name implies, k-means clustering has k clusters, and that's something that we'll set before we run our model. And I'll talk a little bit later about how we're going to set k to be the right value. The way it works is, first we're going to do an initialization step where we just pick some random data point for each cluster to be the starting center of that cluster. And then we're basically going to alternate between steps 2 and 3. In step 2, we're going to assign each data point to the closest cluster. And note that at the beginning, the distance to the cluster will just be the distance to the random data point that started the cluster. But afterwards, we're going to actually define some cluster centers. And so in that case, it'll be the distance between each data point and the cluster centers. And then with all our data points assigned to each cluster, we're going to re-update the center of the cluster. And we'll have some loss function that we're trying to minimize. And we will update the cluster centers so as to minimize that loss function. And we'll continue steps 2 and 3, alternating back and forth until we converge. So what does this look like in math? Well, before we can actually do any of our modeling, we need to come up with some sort of distance metric. So how far away are 2 points? We're going to end up using the L2 norm, or the Euclidean distance metric. And so for 2 data points, x and x prime, the distance between them is the square root of the sum over all dimensions of the difference in between how far they are away on that dimension squared. But we can use any distance metric that we want, and we'll just get slightly different results. The reason this is sort of the normal distance metric to use is it's the Euclidean distance metric, which represents the length of the line connecting x and x prime. So that's sort of the natural distance that we think of between 2 points in space. So another notational issue before we explain the model, we're going to denote the category of the data point by a one-hot vector, similarly to how we had y as a one-hot vector in some of our past models. And it'll be all zeros, and there'll be a 1 in the jth place where the ith data point is in class J. So that's how we'll represent that a data point is in a certain class. Great. So remember, we have 2 steps, and I'm going to call step 2, we're going to call it assignment, and then step 3, we're going to call it update. So first, how are we going to do step 2? So we're going to go through each data point, and for every data point, we will set there R vector, and the cth component of the R vector will be 1 if that C minimizes the distance between the cluster center and the data point in question, and otherwise it will be 0. So in other words, we're just going to assign the data point to the cluster of whose center it is closest to. Great. And now let's talk about how mathematically we do the update. So we want to minimize a loss function, and the loss function that we're going to use is the sum over all data points and then here we sum over all classes. This is just sort of for mathematical convenience because then we're going to multiply by R and C. So only one of the terms in this sum will actually be non-zero because R is a one-hot vector. So only for the class that this data point is in will this contribute to the loss, and it'll contribute the Euclidean distance between the data point and the cluster center squared. And that makes sense because we basically want clusters so that everything is really close to the center of their cluster, which is exactly what this loss function gives us. So now, how do we know how to choose our cluster center? Well, we'll differentiate the loss function with respect to our cluster center, and then we'll use that to solve for the cluster center. Note here that in this inner sum, the only term that matters is the one where C equals I, because we're taking the derivative with respect to the ith cluster center, so the rest of the terms in this sum have no dependence on the ith cluster center. So we essentially just get rid of this sum, and we only care about the ith term, and if we differentiate that, then we get negative sum over all data points of 2Rni times xn minus mu I. And I've written the L2 norm out here in vector form, because I think it's a little bit easier to see how we get this derivative, but it's just chaining together that the derivative of the dot product of a vector with itself is just that vector, and then there's a leading negative that we pull out into the front. So now we're going to go ahead and solve for mu I. We will add mu I to both sides with the respective coefficients in front. And then since mu I doesn't depend on n, we can pull it out of the sum, and then we divide both sides by the sum over all data points of R and I, which gives us that mu I is equal to the sum over all data points of R and I xn divided by the sum of all overall data points of R and I. Note that the sum over all data points of R and I is just the number of data points in category I, and the numerator, the sum over all data points of R and I xn, is just sum of all xn such that n in category I. So we see that mu I is just the average of all the data points in that category, which is a pretty intuitive result. Now, the next thing that we want to show is we want to show that this algorithm converges, because I said that earlier, but I didn't prove it. First, my claim is that both the assignment and the update step minimize loss. We know the update step has to minimize the loss because that's how we solved for the update rule. Now, let me explain why the assignment also minimizes the loss. Recall the loss function is this one right up here, and suppose that our assignment procedure didn't minimize, suppose our assignment procedure didn't minimize the loss. So there's some other assignment of the data points to the classes, which is different and actually minimizes the loss even more. Well, that means that by switching some of the data points into different classes, we'll actually end up with a lower loss, which I claim is false, because the way that we assigned our data points was we put each data point in the class whose center it is closest to. So if we were to move that to a different class, then it's actually going to have a larger distance to the center of that class. So if there's some other assignment of data points to the classes, that's going to have overall higher loss. So we know that both the assignment and the update minimize loss. That means that after any step, if we've either switched our cluster centers or switched our data points assignment to clusters, then that means we've moved to a situation with lower loss because these steps minimize loss. So there's no way for them to change something and then increase loss. We also observe that there are a finite number of states, and what I mean by state is an assignment of all the data points to categories and also category means. Note that assignment of data points to categories is discrete, and although the cluster centers are technically continuous and can be anything, they're only going to either be assigned 1 to exactly the value of one of the data points in the random initialization, or 2, the average of data points in a class, and there's only a finite number of possibilities for which data points can be in that class, so there's only, for all intensive purposes, a finite number of possibilities for the cluster center. So we know there's a finite number of states, and at any state, at any step, either the assignment or the update step, either the algorithm moves to a new state that must have a lower loss, or stops and goes to the same thing. And if it goes to the same thing after the assignment and the update step, well, then we know that it will just continue to do that, and so it's converged. So we know that the algorithm must converge because either it will continue to move to a state that is at a lower loss, and then eventually it will run out of those states because there's only a finite number of them, or it will find some state that it continues to stay at, which is also convergence. Now, we're not guaranteed global minimization of the loss function, though, in our convergent state. We know that it's a local minimum, and what I mean by that is that there's not some way of changing the cluster centers or changing the assignment of data points to cluster centers that will be better, because if that was true, then the assignment or the update step would change. So we know that it's better than the other sort of similar solutions, but we don't necessarily know that it's a global minimum, like the best possible solution. So usually when we have this sort of issue, the technique that we use is random restarts. So we'll just run the algorithm a bunch of times, and we'll start it in different places, and then we'll take the best outcome. The other thing that I talked about but didn't really discuss is how do we choose our K? Usually what we do is we try running it with a bunch of different cluster sizes, and if you graph the cluster size and the average loss over that cluster size, you'll usually get a graph something like this, and there'll be what's called a knee or an elbow in the graph, where the graph kind of sharply changes slope. And so you can pick that as the cluster size. Why does this make sense? Well, this says in this part of the graph, if you increase cluster size, you'll drastically decrease the loss. So it makes sense to do that. But after the elbow or the knee, you're not really getting that much benefit from adding clusters. So it doesn't really make sense to increase the cluster size past that. So two other things that are, key terms that are probably worth mentioning are k-means plus. So as we discussed, the original initialization of the cluster centers is just random data points. But k-means plus is a different way to initialize. And after you pick each data point for the initial cluster centers, you choose your next cluster center based on a weighted probability, where the data points that are further from your cluster centers that you already have are weighted higher. So you're more likely to have your initial cluster centers be more spread out, which is better, because if you put all your initial cluster centers in the same place, well, those are probably all in the same cluster, whereas if you put them in different places, they're more likely to be in different clusters. So the other thing that I wanted to talk about was k-meteoroids. K-meteoroids is a different way to do the update step. Currently in our update step, we just take the mean, and that's our new cluster center. In k-meteoroids, you consider all the data points in the class, and you check which of those data points would minimize the loss, and you make that the new cluster center. So your cluster center is restricted to being one of your data points. I like to think about it as sort of analogous to the median as opposed to taking the mean. And it'll just change your behavior of your k-means algorithm a little bit.